So once again, hello everyone. I think we are going to start. People can join in. So welcome to this webinar on the NIRS Brain Analyzer Toolbox. Today's webinar is done by my colleague, Jonathan Parry, from our newly established Houston office. We are recording this video. We are going to upload this video on our support site. So if you are only able to attend a part of it, or if something is not clear, you can always refer back to the video. Some information before we start. You will all be muted. However, if you have any questions, please write it in the chat window. We will try to answer as much as we can at the end of webinar. If we are not able to answer any of your questions, you can always write to us and we will make sure your questions get answered. So let's get started and invite John to start.
Thank you, Mahipal, and hello everybody. Thanks for joining. So today, just as Mahipal mentioned, if you do have questions, go ahead and ask them in the chat bar. There will be a lot of opportunity for question, and we'll only actually be able to answer probably a handful of that online. If we don't get to it today, we will be happy to answer it offline, so just via our support site. So if you do have any questions that go unanswered, we'll try to answer them offline, and if you don't hear back from us, feel free to send directly to support. That being said, today's talk will be over the NIRS Toolbox, which I imagine a handful of you guys have used. The Toolbox itself was written by Ted Huppert at the University of Pittsburgh Medical Center and has just gone through a revamp of the name. So it's now also known as the Brain Analyzer with a clever IR at the end for infrared. The toolbox itself is an object-oriented MATLAB toolbox, so you do need MATLAB to run it. Your data and pipeline will be actually created into objects. Each object has a uniform structure. Each object has properties or methods. Properties are things like, if I were an object, I would have a height, a weight, things like that. And methods are things that I can do. So I can give a webinar or I can run. In this case, my example here is my name is John. If I call John.height, it would tell you that I'm 5'8". Unfortunately, I don't know that in the metric system. So for everyone using the metric system, I apologize. I'm not very tall. I also have the ability to run. So if I want to call a method, I would say John.run. I put the little parentheses, and that would make me run. Give me one moment while I clear that on my screen. There we go. The presentation will be used to understand how the toolbox actually formats data. It's going to show you how to process a pipeline, how to walk through a standard pipeline in the NIRS Toolbox. So this will be, it will be a full pipeline, but it will be limited to the kind of the bare basics. There is a lot that you can do with the toolbox. You want to be able to understand how the pipeline transforms data. So periodically, you're going to want to actually view your data. And then also, we'll be looking at statistical and processing, a little bit of theory, but this will not be the bulk of it. So if you have questions as to why you would do certain things, if you have questions as to kind of the background of the statistical analyses or the processing, we're not going to cover that today. And then finally, we will answer all questions that we can, but there's going to be a lot that we likely can't answer today. Forgive the noise in the background. So we also will not cover basic MATLAB. So if you need help loading data, if you need help with various types of MATLAB code, this is not going to be the case for that, but it will show you how to write the NIRS Toolbox in MATLAB. And we also won't be listing any citations or going through any research articles on various properties of this. In running the toolbox, we do suggest using at least MATLAB 2017 or greater. There's consistent updates with the toolbox. Dr. Huppert puts these out regularly. You can actually get a kind of a GitHub account for the toolbox and periodically update. You will also need various MATLAB toolboxes in MATLAB. So you'll need the statistics toolbox, I believe the signal processing toolbox, and things like that. Usually when you download it from a university license, these will be included. Okay, so the next several slides I'm going to run through quite quickly, but I want you to get a general idea of how massive this toolbox is. So what I'm going to show you is one of the folders in the NIRS Toolbox, and keep in mind there's about 5 or 6 of these folders. So each one of these screens will list all of the possible functions that you can call in the toolbox, and specifically the NIRS folder. However, there will be other options outside of this. I'm going to pause for a couple seconds on each of these screens, mainly so that when you rewatch the video, you can screenshot these, but I will not be talking about any one of these in detail. So this is what I'm going to call the API. So here we go. So this is the first page. And again, I'll go through a couple seconds on each slide, so bear with me. And this will take a little while. All right, so I'm not quite sure how many pages that was, but that was probably over 100 functions. Again, that is one folder. There are several other folders that you can actually use. The folders range anything from what's called advanced, so more complete or more higher level statistics. They also include external toolboxes, so you can use Homer 2, you can use EEG toolboxes, things like that. All of these are available within this. That said, it's housed in a certain structure. So here on the right side, you'll see I have NIRS Toolbox 1. I actually have it designated as NIRS Toolbox 1 because I have an older version that I keep for my own purposes. But you can name this folder whatever you want. But within the folder, you'll have various subfolders, and most of them are followed by a +, advanced, +, DT series, EEG, NIRS, etc. Within each of those, you actually have several subfolders beneath that. In order to find out exactly what you need exactly what you have or exactly how to call it, you will actually have to do a little digging yourself. So I'm showing you this to give you a kind of an understanding of how to use it yourself. For example, if I were to call a function, I would start with the external folder of NIRS, right? And then I'd dive into the subfolder. It would be NIRS dot, and I'd go to the subfolder, and then it would be NIRS dot core dot whatever function I want. So you'd actually have to call your functions based on their folder location with a kind of a dot notation of sorts. If you're looking at, once you have an idea of where things are and how to kind of navigate the folders, the toolbox itself, when you run it, will create what is called objects. In MATLAB, they have kind of a different style to them, but within this, you can actually find each of the objects. Each of the objects types, let me put it that way. Inside of the NIRS folder and within the core subfolder, you'll see all these little @ symbols, and you have channel F stats, channel stats, connectivity stats, data, blah, 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 you keep going. There's also a table option at the bottom. Each of these are the possible objects that you can build or that will be used. Some of them you may not use directly. They may be used in the background. If you need more information on them, you can actually open the folder, and there's usually a function within that that has a nice little cubic shape to it. You open that up, and a lot of times you'll have a nice comment section. Not all of them do. If you have trouble with it, you can actually create the variable. In our case, in a little bit, we'll actually create a data variable or a data object. And then in your MATLAB command window, you can write help space the name of the variable, and a reference page will pop up. So that's actually quite useful. This is actually what the reference page looks like. Not all of these will have a reference page, but most of them do. So in this case, I actually make a variable called raw, which I'll show you to make here in a little bit. And then once I have it made, I just type help raw, and I'll get a link to this page in the command window. These are very useful. If you notice, we have properties listed for the object, and then we also have methods listed for the object. What that means is each of these properties, if you load it in, they'll have usually a default value, but you can also change these manually or through one of the functions in the toolbox. And then additionally, you can draw or call a method, in this case, draw. For a data object, draw would essentially be graphing. It'd be plotting your data. For other types of objects, it would be slightly different. So when we load the data, so this is the first step. We have kind of an understanding of the folder structure. We have kind of the idea of what the toolbox is trying to do, but we need to actually load in our data now. So there's actually several ways that you can load data depending on what type of data you have. Dr. Hubbard put together a load directory function, which is kind of an umbrella term because within it, it will actually call another function. And that other function is very specific to what file type you have. So if you have a NIRx file type, there's actually a load NIRx function. If you have a .NIRS format, it's a load .NIRS function. Artenis is load oxy3. Hitachi is load CSV, I believe. But each of these can be called within this load directory option. I highly suggest, just from my own experience, that you work with the .NIRS format. There is a conversion script available on the support site. You can run that on your raw NIRx data. It will convert to .NIRS, and you can call the load .NIRS function. What that looks like is this code at the bottom here. So what I want you to kind of picture is that what's really nice about the toolbox is you can structure your folders however you like. I really, for most types of studies, especially if it's between groups, you have a group level and then you have a subject level. So in my case, I kind of put together a fake folder format here for you, but you notice I have a control group and I have a pathology group. Within that, I have 6 subjects, and that's my subject level. Within the subject folders, then I actually have my experimental data, my raw data in it. To actually call it, what I'm going to do is open up the folder that houses the control or pathology. So if you can picture an experiment folder that houses that, I'm going to open it to that level. I'm going to create a root directory by using this built-in MATLAB code, which just basically gives you a pop-up, and it asks you for your working directory, so PWD, and it's just going to ask, please select folder. So pop-up comes up, you select the folder, and you stop wherever you have the group level. When I actually call the load directory, I'm going to input this root directory. So it's going to be NIRS, which is that NIRS folder, if you recall. Then there's a subfolder called IO, and then there's a function within the IO folder called load directory. The parameters for that can be found in the load directory function in the comments, but it can be a little confusing to read through those sometimes. So what it's asking for is the root directory, which I selected already. Then it's asking for what structure are my folders within that directory. And I'm going to say the first folder it's going to reach is my group. All folders within that will be considered subjects. And you can name those whatever you like. I believe you can actually do more levels if you want to do more levels, but I think it's pretty standard to do group and subject. After that, it's going to ask what function are you actually using to call. You don't actually have to list this. If you leave it blank and you don't select what type of data format, you don't select what kind of load function you have, it will look for all 4 of the functions listed here, NIRx, .NIRS, Artenis, and Hitachi. If you have one of them, it will load that one. The problem is, though, if you have 2 of them, it will load both of them separately. So in that case, it will be, let's say we have a .NIRS and a raw NIRx format. It will actually load both of those as different subjects, which can get kind of confusing. So I do suggest that you specify which file you're loading just in case. And again, I like working with the .NIRS format. It's fairly standard. It does tend to house everything, and in my mind, it's a little clearer because it's all concise. Once you select the function, you have to select the combined file extension. So I'm loading a .NIRS and I'm searching for something that ends in .NIRS. Once you call that, you will create a raw data object. And again, this is what it will look like. So within it, you'll have a description, which will be the file name, the data, which will actually be a double matrix. And I believe it's concatenated wavelength 1 with wavelength 2 by columns. The probe is going to be your source and detector layout. So usually that if in a NIRx system that's done with a with NIRSite, it creates a probe info file. The time is simply just converting your frames to seconds. FM means frequency modulation. If you're doing continuous wave NIRS, which all NIRx systems are, that will be blank. Your sampling rate is next. Stimulus will be all of your event markers, and that actually has several fields in and of itself. And then finally, you'll have demographics. Demographics will be like age, male, female, etc. And then you can draw your data, which again is going to be plotting it. So we have that in, we've loaded our data. The first thing that needs to be done, and I think a lot of people kind of skip over this because there's so much going on in the lab, you want to look at the data. You think you loaded it right every time, and it's not always the case that it was loaded right. So you want to make sure the structure's right, everything looks the way you expect it to look, there's no weird anomaly or anything like that. So there's actually a function call in the NIRS toolbox, which is very handy and very simple. In the NIRS folder, there's a function called create demographics table. It literally just prints out information about each of your subjects. And it's going to be based on that folder hierarchy when you loaded it. So here I'm saying my demo for demographics equals my NIRS folder. Within that, there's going to be create demographics table, and I'm going to call it on my data, which again, I named raw. So the group will be, again, the first folder in that folder hierarchy that I called in the load function. And then the subject will be the second hierarchy. And it grabs the name of those folders. So it's the first 6 are out of my control group. So you see subject 1 through 6 are all control, and the second 6 are out of my pathology group. I believe in this folder I was both control and pathology, which may actually be correct, but to simplify it. So after that, you'll want to actually see the data. So we know it's structured right, everything's good, but now we actually want to see, okay, well, let me plot it and see what my data actually looks like, what the raw data appears to be. Is it within range of what I expect? So all the data objects have a .draw method. What you'll have to do is basically grab your data variable, and you're going to select your subject number. So I don't believe you can actually do all subjects at once, if I'm not mistaken. So you do have to select what subject you want to view. And usually one subject would suffice, but you may want to view a couple of them. Then you'll put .draw, and then you'll select what channel number you want to plot. If you don't select the channel number, you can just leave that blank, and it will actually plot all channels, but it gets a little messy. What you do see here, though, is I have my time in seconds. I believe this is voltage here. Then you have all my stimuli coming in, and you'll notice the default values for these are stim channel 1 and stim channel 15. The stim channel part of that is defaulted by the NIRS toolbox. The number next to it is the value that you sent on your trigger. So there's a good chance you're going to want to change the names of these triggers, but we'll actually get to that here in a bit. But for the sake of distinguishing between types, it at least does that. And you'll see they alternate in color. If you set the duration of these to a different value, depending on what load function you use, the load.NIRS function will create a stimulus duration equal to the sampling rate. So, or seconds by the sampling rate. So if I had an 8 Hz sampling rate, that's 1 divided by 8 is about 0.12, and that value would be the duration of each marker. With the load NIRx data, you get a default value of 1 second. So you probably, if you have a longer stimulus duration, you may want to adapt that down the way. However, the default value will at least mark the values. Once we go from there, you can also use just the basic MATLAB code. You don't have to rely solely on the toolbox. So there's always the plot function. For me, I think this is actually, at least for seeing the data, is much more intuitive because you see all channels. It's a little bit more spaced out. The event markers aren't blocking anything if you're not so interested in that at the start. So in order to plot it using MATLAB, you just call the plot function. You'd select your raw variable, which is your data. You'd select the subject number, and then you do .data, which is the data variable, which is housed within that object. And you get this lovely picture of all the channels. Again, here we could select the channel number if we wanted to only view a handful of channels or just one. The other option you have is to actually see your probe, which again can be handy. In fact, I've actually messed around with my data sets quite a bit, and I've changed the probes on purpose to show bad channels and things like that, and I forget which ones I changed. So it's actually quite handy to compare and make sure all these line up. So in order to actually draw the probe, keep in mind it's a 2D probe, but it's fairly obvious as to what's going on here. The top is going to be the front of the head, the back is the back of the head, the left side is the left, and the right is the right. Again, you'll select the variable raw, which is your data. the subject number, doesn't have to be 1, you can select whatever subject you want, dot probe, which is one of the fields within the variable, and dot draw. And again, you have that function built into this probe object. So here you get this lovely, and this is a motor montage to give you an idea. The left side is the left hemisphere, the right side is the right hemisphere. It's actually one of the default montages that comes with NIRS. So once you have that, I mentioned that the default value for the stimulus names is stim channel followed by whatever number you sent. This can be kind of strange and annoying sometimes, and you likely want to change it. So at this point, we're going to start talking how to view different things, but also how to start our pipeline. So we've seen our data, we've played with it, we've explored what the probe looks like, what the data looks like, where the stimulus are, all that. We have a good understanding, everything looks good. Now we're actually going to want to start processing things. So I always say that kind of the processing steps at the start are nowhere near actual data processing. It's usually just setting up the data to be processed. One of those steps is getting these condition markers named appropriately so that we know what we're dealing with, and especially if you have a larger lab that other people are going to be looking at this. So in this case, I want to see what these stimulus names are. So I know for a fact, just based off of this, they're named stim channel 1 and stim channel 15. So after that, we want to actually find where those are located. Those are located in the raw variable of, I'm looking at subject 1 again, dot stimulus, and the stimulus has a field called keys. The keys are the names. There's also a value called, a field called values, which will actually contain all of the numerical information. But I'm worried about the keys right now. So if I want to change that, I actually will call a function called rename stems. And again, that long list of functions, this was housed hidden within that. What I'm going to do here, and this is jumping now into the pipeline, I'm going to start my first step of the pipeline. I'm going to call the method, which is NIRS.modules.rename stems, and I'm going to call it on nothing. I'm just creating an empty placeholder essentially. And then I'm going to save it as an output. The default for the toolbox is saving it as the output J. You can call it whatever you want. If you want to call it job, if you want to call it whatever you want. Pipeline or something like that. But the default value in the toolbox is J, and just for that, I'm going to keep it as J during this entire talk. So this rename stems, if I were to open it, it actually has some commentary that tells me what properties it has. One of those properties is list of changes. The list of changes is asking, okay, what is the starting values, and what do I want to change those starting values to? So the starting value, again, for the first one, was stim underscore channel 1. So I put that in quotes, comma, and then I apply the change. I make a new row using the semicolon, and then I do the next condition. If I had 8 conditions, I would have 8 rows. And I'm going to have the first column of these rows is my initial value, what it started out as. The next row is the new value. Be careful here, because if you don't get the text right, especially on the initial value, it won't register, because if I instead just put channel 1 instead of stim channel 1, it wouldn't make a change because there was no channel 1 to begin with. Once I select the list of changes, it saves to that variable J, because I have J.list of changes equals, and I make the change. Then I actually have to run this value. Whenever you create a pipeline in the toolbox, you actually have to call it. Nothing happens until you actually hit run. So each one of the jobs, or each one of the jobs in the pipeline, has a method called run. So I do j.run, and I select what do I want to run it on. I want to run it on raw, and I'm going to put the output as whatever I want to call it. You may actually put raw edit. You may resave raw. I do suggest making a new variable and always maintaining your original data variable, but you can call it whatever you like. Condition names may have actually been a poor choice on my part, but raw edit or something like that may be a better choice. So we have it in, and keep in mind now that we're building this pipeline, the pipeline in and of itself is an object, but it's kind of a slightly different object as far as the toolbox attributes it, because it doesn't have its own object folder and all that, but it is building an object. You can think of it as a to-do list. So each time when I start it, I'm going to call it on an empty parentheses. That is always going to restart my list. On future ones, I'm going to have to put in something into those parentheses. But basically, when I start the empty list, that's my first step. As I go down, I'm going to take the output of that first step and put it into the input of the next, into the next, into the next. I'm going to make my very long pipeline. And then at the very end, when I want to run it, I'm going to put j.run, and it will run the entire list in one go. So this is how we start. So again, we're going to start with that same first step, rename stems. So I call j equals, find whatever method I want to call or whatever module I want to call. In this case, it's the NIRS folder within the module subfolder with a function called rename stems. Often the first step of the pipeline, as I mentioned, I call it very pre, because you're essentially setting up your data to be processed. People, you can call it pre-processing or whatever, but it's, in my mind, it's kind of a separate task than full-on processing. So here we're going exactly back to where we started. So I want to change the name of these stimuli. So I create my open variable, save it as j. I adapt it as I need, and it becomes, now stem channel 1 will become my left hand. Stem channel 15 was my right hand. That's what I was tapping my left and right hand during this. If I'm curious now as to what j is, I can actually click help space j once I've saved it. And then you'll get actually some information. If it exists, you'll get some information. So now I want to actually add the next step. So adding the next step, I decide I want to actually trim my baseline. Trimming the baseline means essentially I have my full data set, and I want to trim at one end so many seconds and at the other end so many seconds. So I'm going to take the output of this, which again was j, and I'm going to put it in here now. So now I'm putting the output of the first one into the input of the second. I'm calling NIRS, the NIRS folder, the modules subfolder, and trim baseline is the name of the function, and I'm going to resave the output now. So now I have two steps. I have my current step, and I have what's called a previous job as my first step. And this one actually happens to have two properties as well. One is called pre-baseline, one is called post-baseline. Their default values happen to be 30. I did nothing for that. That just happens to be how the Toolbox has created it. And let's say I want to change those to 10 and 25 seconds. I would make these lines of code, and that would update it. So during the whole process of creating your pipeline, there's a good chance that you're going to want to check periodically what's happening to your data to make sure that everything's going correctly. You're not just trusting it blindly. So one of the ways to do that is I can call this run method at any time. I can say j.run anytime I want, and it won't, nothing actually happens to the j variable. It will actually maintain exactly where I left off on the j variable, but it will give me output at that step. So here, let's say I've renamed my stimuli, I've trimmed my baseline, and now I want to see what my data looks like. I would just select j.run on my variable, on my data, and I would save it as some output. You do have to save it as an output in order to view it, unless you print it on the screen, and then it's difficult to view anyway. But you're going to want to save it as a variable, and you'll probably want it anyway for future reference or for plotting purposes or something like that. So what I'm going to do is j.run on my variable. I have my output, and then I can plot my output. I can open my output in my workspace. I can view it. I can check it, that everything's working properly. Keep in mind as you go through this that the input into a function may have different properties and methods than the output. So as you go, different things will occur, different things will change that you may not be able to draw the output, or you weren't able to draw the input, but now you can draw the output. As you adapt your data, they'll have different properties here and there. So it's also worth just exploring to see what changes throughout that. And also keep in mind, you do not have to use run after every step. It is likely only the case that you're going to want to use run periodically, and probably at the start of your experiment when you're piloting it, when you're trying to figure out what's happening, that you're making sure your pipeline is correct before you actually dive deep. And also keep in mind that oftentimes the draw function has to be subject specific. That's basically saying if I have 10 subjects and they each have a different montage, I can't draw one montage. It's going to be 10 different montages. So you have to select which one you want to draw. And you can select all 10 individually, but you wouldn't be able to draw them all together. Okay, so now we have renamed our stimuli, we have trimmed our baseline, and now I actually want to create optical density. And if you're not familiar, optical density is a unitless zero mean log change of your data. So you start with raw voltage as your output from the system, you collect that as your raw, and then you actually want to basically make a relative change, which will then be put into the Beer-Lambert law for concentration changes down the way. So there's a function called optical density in the NIRS folder under the module subfolder, optical density. I now take the output of this trim baseline and I put it into optical density, and then I'm going to save it as J. Again, you can plot this. I think this is actually just calling plot, and then you select after you run the task, you plot it here, and you can get a visual of what optical density looks like. And for a quick comparison, optical density is here, and if I go back just a few, right there, there's your raw voltage. So you can see a very clear difference in the transformation of your data. And there we are. So the next stage is usually a filter. You can put often the bandpass filter is the go-to. From what I've seen lately, though, it's been pushed that pre-whitening is probably a better option. I'm going to discuss pre-whitening here, but also keep in mind that pre-whitening is actually performed down the way. So if you use a bandpass filter, you will not use pre-whitening. If you don't use a bandpass filter, you are free to use pre-whitening. And my understanding of it will be explained here, but it seems to be the way to go. The idea behind it is that when you're performing statistical tests, you're assuming that none of your data is related to the other data. However, we're looking at time series data, which means that whatever I did at 10 seconds, it affected what I was doing at 11 seconds, which affected it slightly less what I was doing at 12 seconds, slightly less at 13 seconds, and down the way. So you're correlated, at each successive time point. Pre-whitening is an attempt to remove this connection between time points. So the kind of joke is we're normalizing the data to apply the statistical tests more appropriately. So you're almost changing your data more than it was originally to perform correct statistics, rather than changing your data less to apply inappropriate statistics. So there's obviously a weight there, but this is apparently the better way to go. And again, we won't go into detail on why or state any citations for that, but there's plenty on this. This is the idea behind it. So if I have what this graph shows is that I have time point 0 on the x-axis all the way to 21 seconds away from that time point. So let's say I'm considering time point 10. I'm going to consider time point 10 to be time point that's going to be my starting point, 0. At that exact point, I have a correlation of 100%. That means time point 10 is 100% correlated with time point 10. As I move down, I'm going to correlate time point 11 to time point 10, time point 12 to time point 10, time point 13, 14, all the way down, and it's going to go up to 21 seconds after time points off of time point 10. And I'm going to correlate those and see how closely correlated they are. As you notice, there's actually quite a bit of correlation as you go. It actually maintains well above, for many of the channels, well above 90%. But it does fade off. It does drop. The goal in doing this is to actually correct this. In correcting it, we're going to find something like this. So at time point 10, you still have 100% correlation. After that, you actually are very close to 0% correlation as you go past that. The math behind it has to do with some solving for matrices to receive an identity matrix, and there's some fairly complex mathematics who I am not the guy to go to for that. But the general idea is here. Basically, I'm removing this gentle slope to apply this drastic drop off in correlation between time points. And again, that will remove autocorrelation from your data to allow the statistics to be applied more appropriately. So in calling this, if you wanted to call it individually, this function is AR_pre-whiten, and it's in the advanced.nirs.modules, which again is the advanced folder, NIRS subfolder, modules subfolder, and this is the name of the function. And then I would input whatever job pipeline I had. This said, I'm going to apply this GLM function at a couple slides from here. The GLM function actually already utilizes pre-whitening if you leave the default value of ARILS as the solving function. So if we maintain that and you don't change that, this is actually already applied and you don't have to worry about it. If you change it, there's a good chance you may actually have to apply this. So going back, we talked about pre-whitening, but we actually did not apply it. What I want to actually see though is I've gone from raw voltage to optical density, which again is relative change. Now I want to turn my optical density into concentration values. To do that, you have to perform the Beer-Lambert law. So I'm going to take the output of my optical density and put it into the Beer-Lambert law. The Beer-Lambert law is found in the NIRS folder under the modules subfolder, and then Beer-Lambert law function. The graph looks something like this. This is going to be hemoglobin values. I believe it's actually oxygenated hemoglobin values. I did not state that. Once you have the hemoglobin values out, there's a good chance that you're going to want to run a GLM. There may be other ways you're approaching your data, but for our sake today, we're gonna cover the GLM. In the solving method, in solving for the model, the idea is that you're going to try to compare the data to the model, and you're going to shrink or grow the model to fit the data more appropriately. And these are called your beta values. They're essentially coefficients or weights, however you want to view it, but it's basically how well your model fits your data at that condition, at that channel. Once you get those values out, that's usually when you'll apply a statistical test. So you usually do a t-test, an f-test, something like that. We're going to cover the t-test today, but you can do an ANOVA down the way as well. It's a little tricky, but we can cover that at a later date, or if you have questions, you can ask. But we'll cover the t-test today. So in implementing the GLM, you will need some a priori information, basically what you expect your data to do. So that way you can choose the appropriate model. In order to call this, I'm going to have the NIRS folder, the module subfolder, and then the GLM function, and I'm going to input my full pipeline. So I've been building this pipeline the whole time, and I'm going to input it here. This will be my final step. So in calling this GLM, you actually have several model options to choose from. These can be found in the GLM function, though I think it gives you an example for that. But here I'm actually going to show you what they are. So the first one is a boxcar. It's pretty much the most basic you can choose. It's just a square box. And what it's saying is whenever my stimulus starts, I'm expecting my data to make a square box, which is kind of correct, but obviously not, because we're dealing with blood and it doesn't create these sharp angles. So in order to view it, I'm going to have boxcar.draw, and I actually saved the variable boxcar by calling nirs.design.basis.boxcar, and this is the folder that you will find all these in. So the boxcar is this on the left. If you notice, there's about a 2-3 second delay. It shoots up to 1, it goes over till about 8 seconds, drops back down, and then it's done. Again, it's kind of correct, but really not too great. The often used canonical basis function is usually referred to as the hemodynamic response function. However, you will see others referred to as that as well. Has a little bit more shape to it and is likely more appropriate for most tasks. So you have a delay, it shoots up, reaches a peak, drops down, it overshoots and comes over. This is the kind of go-to as far as FNIRS goes, and MRI, I believe, as well. The next options you have is the finite impulse response, and this actually did not have a draw function, so I did my best. If you can picture each of these blue lines as little finitely distanced, infinitely small dashes going up, each one will be weighted to kind of make a shape. So I did my best there to draw it, but it's probably not the ideal version. The next is a gamma function, which looks quite similar in many respects to the canonical. However, you're missing an undershoot. You're missing a little more variety in the tilt of the peak. You also have the general basis function, which I believe is actually identical in many ways to the canonical, but I haven't verified that. And then you have this vestibular basis function, which has a little bit more of a delay at the top. I've been very intrigued by that lately, but I haven't really seen anybody use that. All right, so now we have an idea of what the shapes are to call them. when I actually run the GLM, you get an output. The output, in my opinion, is fantastic. It's a very SPSS style table that comes out. What you have is going to be your source and detector combos. So source 1, detector 1, that's considered a channel. You have what type of hemoglobin it was, HbO and HbR. It does not run on HbT, so you would have to run that separately if you wanted, but it does have the two big ones. And then it'll have the condition. And you'll notice I actually did not change the condition names here, but for our sake today, it's left and right. You'll have the beta values for those, the standard error, the T statistics, the degrees of freedom, the P's, the Q's, and the power. So this prints out everything you need. The one catch is the T statistic is actually set as to how it's run. So if you want to change how it's set, I think it's actually run versus baseline. I'm not certain of that, but I'm fairly confident in that. If you want to change how that's run, we're going to cover that in a little bit. So you actually have to run it slightly separate. The other option you have is to actually print the beta values. Essentially, you would have the output of the GLM dot draw. When you draw it, it will either draw betas or T statistics, and within that, there's a parameter for selecting beta or T statistics. So as I mentioned, by default, the GLM module performs a t-test. You can also select to run other sorts of tests, f-tests, something like that. If you want to run the t-test separately, you want to actually contrast different things than what it defaults to. This is how you would do that. So you'd actually have to select or basically claim a contrast matrix or vector. So what I did here is on C, I have two conditions plus a control. So I have my left hand, my right hand, and a control. That's for the first part that I'm going to contrast against the second part. So the first 3 is the first part. The second 3 is the second part. And this is my left hand, right hand, control. Left hand, right hand, control. What this is saying is I'm going to contrast my right hand against my left hand. And if I wanted to do it the opposite, I could actually shift. I would put this 1 here on my left hand, and then I'd shift to this -1 here to my right hand. I'd do the left versus the right. Once I run that, I'm going to select the GLM output, and I select the subject. I believe you can do just as a whole, but I may be mistaken on that, so I don't think you actually have to select the subject. But then you do .t-test, which is a method within the GLM, and then you input the contrast. And you have to save this as a variable. So I put contrast stats, you can call it whatever you like. This output then has a draw notation, and I can do that right here. It also, I believe, has a table notation. In replacing contrast stats dot draw, I can put contrast stats dot table. So either way you want to view it, you can get that out of. But this is a fairly intuitive graph. The deeper red it is, the more the greater the value of the T statistic, or in this case. The table output would essentially be this exact output as we saw earlier. Again, you'd call the variable, here you do have to call the subject number, and then you just say .table. And you can either save it as a variable or you can print it out on the workspace. It's your choice on that. The last bit we're going to cover is there's a few things that I have yet to be able to find in the toolbox. I was a little bit surprised, but fairly simple things that I could not find. They may be there. I've done quite a bit of digging, but I haven't found it. One of those things is a block average. I haven't been able to find block average. And Dr. Hubbard, I don't know if you are in attendance, but if you are, I can talk to you later if it is there and I haven't found it. So that said, there are many external functions that you can call that do house this. So I actually pulled in Homer2 within the toolbox to do this. It wasn't perfectly smooth to manage this, but this was the output. So based on this, I was actually able to run a block average using the Homer2 toolbox. So very basic. You can see I didn't really filter the data. It's actually, you can still see the heart rate and all that. And it's several channels thrown in there. And it's also oxy and deoxy in there as well. This is the code. So as I mentioned, it wasn't as intuitive as I would have liked. What I had to do is restructure a few things and move it around. But you do have the output for it. Here is actually, let's see, the actual call of Homer2. So this is the exact function out of Homer2. It's called Homer block average. and you just have to find the inputs to add into that. And then you have to plot it at the end, which is what's done here and here. So it's not super perfect or super smooth in that sense, but it's still completely doable to call in Homer 2. And there are smoother function calls and things like that that you can do. So this is the kind of general run through of the toolbox. I hope it can get everyone off and running on it. There is definitely a lot more that you can do with it than what we covered today, but this should at least give you the opportunity and the understanding of where to look, how to call things, what kind of formatting it does, and get you off and running. I do want to mention, you know, you have pretty much anything you could ever want to do with this toolbox, but it absolutely requires dedication of time. There's so many things hidden away in it that you have to figure out where they are. So you have to set time aside. If you're planning on using this, you're going to have to be willing to dig. You're going to have to open up some folders. You're going to have to go through it. YouTube is growing in the options for this. The documentation is growing for this, but it is a lot of digging thrown in. So it's a terrific toolbox to use. Once you get the hang of it, it is very simple to use, but the learning curve can be pretty big, and you will have to dedicate time to get through that. There are other options, kind of in varying levels of performance and usability. So our in-house software, NIRS Lab, is terrific in many respects. We often say it's very, very, very good for preliminary analysis, but when you get, and it's also for NIRx data only, so keep that in mind. But if you are, looking to do group analysis, things like that, it is often easier and sometimes more higher performing to move into things like Homer 2 or the NIRS Toolbox. Homer 2 is a GUI-based processing platform. It doesn't run your statistical tests, but it does house many similarities to the Toolbox, but it does have a few more limitations in comparison to the Toolbox, in my opinion. But there are others out there. You can use many EEG toolboxes now. You can use other things like that. On that note, I will go ahead and end my very long rambling and open it up to questions if anybody has them. Let me go ahead and pull Mahipal up. Let's see here.
Hey, John, I'm there.
You're there. All right.
Very nice. Thank you very much.
Thank you.
So we have at least 2 questions which popped up during the webinar. I will also check if we had questions while registration. There is one which is rather open-ended: how to compare specific brain areas by using regions of interest. So I can comment on that. I think it's really you have to write to us with some more information. As it is, I can't say much, at least.
Yeah, and just to add, I think Mahipal and I actually discussed that prior to the webinar. It's mainly, I don't think the question is specific enough to answer on our end. The question would be, are you looking, because you can just put a source and detector here and a source and detector here, and then you can compare them using either a t-test or something like that. The other question it would be, maybe it was meant that you weren't certain if you were on the region of interest, in which case you'd have to use something like Fold, or within the toolbox there actually is a tool to compare if you think you're within the right region. And then also just what questions are you asking in line with that, because then your statistical test would change depending on your hypothesis and what kind of measurements you made. So that's something, as Mahipal mentioned, we probably have to take care of offline and get some more details on.
All right. So there's one from Shannon. Hi, John. Have you figured out how to remove single trials within a condition, or how to split the trials in one condition?
So actually, Shannon and I had talked about that last week, and I was hoping to get to that this weekend. And I apologize, Shannon, I haven't gotten to it yet, but it is still on my to-do list. So I have those 2 functions that we had spoken of, and I am running through them either today or tomorrow or this weekend, depending on how many meetings and other support cases pop up during this time.
All right. The next one is from Aaron. What benefits do you see of this toolbox over Homer 2?
When I use them, it depends on what I'm trying to get out of it. Homer 2 has been very useful, especially in doing simple group comparisons. I won't say analysis because it actually won't run the analysis. So that's the bit most obvious, is that you can do block averages in Homer 2. You can extract beta values in Homer 2, but you can't actually run the tests in Homer 2. Unless they used to have that function. I think it's disappeared. I haven't been able to find it, and then they may be implementing it again, but I haven't seen it. The biggest thing I've seen is that you have a little more freedom and a lot more options, and then you can run your tests in-house. I actually favored Homer 2 for quite a bit because of the learning curve, but once I got the hang of the NIRS toolbox, I will say that in my use, I use the toolbox a lot more than I use Homer 2 now.
All right. Maybe I was curious, John, regarding the ease of use. Homer 2 has a GUI, so for me, that's rather more intuitive. What do you think about NIRS toolbox?
Yeah, I completely agree. The GUI for Homer 2 is very, in my opinion, quite simple to use. There's a few things on it that are tricky, but for the most part, it's very good. The toolbox has a GUI. I have not really been able to figure it out. It's a little tricky, and that said, I haven't spent too much time on it. So if I spent more time on it, maybe it would grow on me. But I prefer quite a bit more. I prefer the toolbox to write in MATLAB because once you get the hang of it, it's not overly difficult, but it takes a while to get the hang of.
All right. So next question is from Adam. For AR filters, is there a difference between NIRS.modules.AR_IRLS versus AR_prewhiten?
So I believe, well, there is a difference. They're two different things, but I believe the AR_IRLS actually houses a pre-whitening filter within it. The AR pre-whiten filter is just the pre-filter. So the AR_IRLS is a way to solve for your model, and it's fairly complex. You can think of it as a fancy ordinary least squares, if I'm not mistaken. The AR pre-whiten does not solve for the model. It's more of a filter. So one is kind of housed in the other, and it's outside of that, they're different functions. They're different. They serve different functions.
All right. The last one is from, excuse me, I missed where is the screen? Yes. So where can we find the residual error and beta 0 after GLM? It seems there is no such result.
I believe there's a standard error. My vocabulary is horrible, so forgive me on this, but I believe those are not far off from each other. SE is standard error. And again, my vocabulary is terrible. I'd have to do a quick Google to verify that. But I believe you'd see it on this column 6 here in the table. And again, I need to verify that standard error and residual error are the same. So forgive me on that.
Okay. I believe this is it for the questions.
Okay.
Yeah.
All right. Well, I want to thank everybody for coming. I do hope it was helpful. These were questions I've had probably for the last year, and I figured I'd put them into a PowerPoint. There's definitely a lot more that I have, and I'm sure other people have their own. But I was very happy to construct this, and I hope it was useful.
It was very easy to follow, John. It was very, very useful.
Thank you so much, Paul. All right, thank you guys very much for coming. We'll upload the video probably by the end of the week, and it'll be available on the support site. And again, if you have any other questions, you can email support@nirx.net, and we'll be able to answer probably most of them, but we just may need a few more specifics on them. But thank you guys very much.
Yeah, thank you. Bye-bye.